All right, so let us slowly start. And today we have a next session of AI and Digital Science Research Center at TI seminar. And the topic for today is computer vision for medical images. And I'm very happy to have today Mikhail Belyaev, who is a researcher in artificial intelligence, and especially recently, not really recently, but probably last like 7 years, he was working on medical domain. And currently he is a CEO and he's a founder of Ira Labs startup, which has several successful products in the area of medical imaging. And I'm sure that this talk is going to be very interesting for all of us. So Mikhail, please start, and the floor is yours.
Okay, thank you. It's a pleasure to be here with you. I consider this as kind of a present for my today's birthday. It's really cool. So yeah, as Maxim told, I will start with brief introduction. So I actually have three distinct parts of my career. The first one was related to industry. I was a data scientist at a startup company. We developed several machine learning algorithms and also did some consultancy projects with large industrial companies, mainly in Europe and Japan. Then in 2016, I switched to academia and I started my research group in broad area, kind of data science for biomedical data. Internally, we did several pivots to identify an area where we can translate our research into some products or some technologies. So at the end, we identified this area, medical images, medical image analysis, or medical computer vision, as I usually call it. In 2020, when the pandemic started, we identified a demand, and actually it's more or less, it started with more or less local demand, I mean, local in Russia, to automatically process COVID images and make some decisions based on percentage of affected lungs and overall appearance of symptoms. And then, well, 1 year ago, I switched, finally switched from the university to my company. Currently, it's a pretty large company. We have 50 employees. So I have some slides related to the company, and then I will switch to the research part. And I believe this is important to introduce the area. So this is more about my motivation when we looked for the possible area. So as I mentioned, it was really important for me to identify an area where we can produce some real value. So not just research, but research translated to something. And this is more about kind of why we decided to do all this stuff. Basically, there are actually many types of medical images, different medical images. We work mainly with computer tomography. So we can consider this as a 3D image, one channel, so grayscale 3D image. Also, we have some projects with MRI, research project mainly. But basically, this is just a different physical process to get a different, but still one channel grayscale 3D image. So here is kind of a visualization of a CT from chest to pelvis. So why is it important, and specifically CT? This is an interesting graph. So the baseline black line is the number of radiologists in Russia, where the 2010 is selected as the start year. So as we see, the number of radiologists is approximately the same, a slight increase, but the number of CT studies or patients to analyze, this number is growing constantly. So we also see the effect of COVID in 2020, where other imaging modalities experienced a drop, and CT almost doubled the amount, but still the trend is very clear. So the amount of work for radiologists is constantly increasing, and the number is approximately the same. And this is why it can be really useful. So to understand what is one CT image, here is the illustration, right? You need to go through 400 of such images. This is one patient, approximately 400. Usually you need to do it at least 2 or 3 times to analyze different parts of the image. I mean, lungs separately, then soft tissue separately. And during the day, you need to analyze up to 70 such studies, so 70 patients. It's really, really hard job. And so there are a lot of possible sources of mistakes due to limited time for analysis, due to overloads, and etc., etc. And I mentioned this famous quote from Geoffrey Hinton in the abstract of the talk. Indeed, he in 2016, he is saying that AI is so good and radiology is so simple that it's clear that in 5 years, AI will replace all the doctors. In fact, right now we understand that this is not the case. Actually, in many countries, radiologists are still on demand, and actually, despite the number of radiologists increased, there is still shortage. And the UK is likely the most bold example in Europe. Now this shortage is around 25%, I believe, or maybe 30%, and they expect that it will be almost 50% in 2025. So why they still, why AI doesn't process all these images right now? I believe that there are several answers. So the first one is that the medical device industry in general, not only AI, but in general, this is a really slow industry. So it means that we have a lot of regulatory barriers, like we need to get FDA approval or CE mark. And even if we do this, then we need to prove that our services, software should be reimbursed. So it's a different challenge to be paid actually for our software. But this is out of scope of my talk, but I believe that this is an important part to mention. But what is more interesting for us today is that also some reasons are related to AI behind the products. So the first one is that actually product functionality, current product functionality for CT, for example, is quite limited. And Signify Research, it's quite well-known agency, research agency, market analysis agency from the UK. They believe that the majority of current products are too narrow. So they address just one pathology, for example. And this is way too small to replace even a part of radiologist's duty. And actually, the third issue, according to my numbering, the third issue is that the accuracy of models in independent evaluations, I mean, not in some reports generated by a company or by a research group, but independent evaluations, usually on a different data set. And the quality drop is really significant. It means that it's really hard to create a generalizable model and create a product based on this model. So obviously, both last questions can be addressed by some research. And actually, this is the core part of my talk to show you some examples of related challenges and possible answers, which we did and actually which we are doing in our group right now. But before, I'd like to, again, briefly describe the industry itself and actually what's the possible benefits of using AI in radiology. And then I will cover some industry insights. So how this or that research problem or solution can be used or affects the industries of the products. Basically, what we did in what my company do, we process these grayscale images. And first, we highlight some regions with pathologists. So to draw radiologists' attention to this area. Second, we automatically calculate some measurements. It can be linear sizes, volumes, some complex indices, everything we radiologists need to, according to clinical recommendations, we can calculate this. And finally, the third, it's a very important step. We generate the suggestion what to do with the patient. So what is the next step, according again to clinical recommendations. And our core I would say benefit of our solution is that we analyze all clinically relevant findings on a single chest CT scan. So it's not only lungs, right? It's also heart. It's also ribs. It's also vertebra, main vessels such as aorta, and some parts, some abdominal organs, such as liver, for example. So all these organs are important for doctors. So we need to analyze all of them to address this too narrow solution challenge I mentioned before. And we mainly work in Moscow because Moscow has a really huge network of connected hospitals, connected to a single cloud storage. And they have they reduce some regulatory barriers to join this program and to participate in the processing. And they created a contest, actually, an open contest for company around the world. Before the war started, we had several international companies. So, currently, the majority of participants are Russian companies. And from this graph, it's kind of the illustrations that we have more products and we have better products, according to some comprehensive ranking system created by the dedicated research center, medical research center in Moscow. And I will later return to one of our competitors, Zebra Medical Vision. It's quite famous startup, and we had an opportunity to compete with them directly with their core product on vertebral fractures. From the IT point of view, it's pretty simple. So we have CT or MRI machine, then the data in standard DICOM format is transferred to this cloud-based storage, and then we connect to this storage, process the images, generate these results with some annotations and measurements, etc., and also we generate this report, right, with findings and with the suggestions what to do with this particular patient. Okay, so the introductory part is over, and now I want to concentrate on data science and on challenges we need to address to resolve actually industry barriers I mentioned before. So the first thing we need to discuss is the amount of data available for training. So ImageNet is the most famous computer vision data set, and we are talking about millions of images, right? And the size of each image is pretty small. So it's roughly 200 by 200, right? So it means that the balance between in some sense, right, dimensionality, it's not the right term for just multiplying the sizes, but still the ratio between dimensionality of the problem and the number of data available is pretty good. If we check the largest public data sets available for medical images, for example, these brain tumor MRI data sets, so-called BREDS, we see that the number of annotated cases is several hundreds, not millions, just hundreds. From one side. From another side, we work with 3D images, right? So now it means that in some sense, dimensionality is much higher. And in overall, it means that one of the most important challenges in the area is that we lack annotated data. There are several reasons behind. So the first one is that these tasks, annotating, for example, COVID lesions or identifying lung cancer. This is red square. It's likely it's a lung cancer. So you need to hire highly educated professionals. It cannot be crowdsourced like ImageNet was annotated. And we know, as we discussed, that there is a clear shortage of such professionals, even for their day-to-day duties, not to annotate some images for AI. The annotation is really time-consuming, especially if we want to create some 3D masks like COVID-19 lesions colored in orange in this example. And as a result, from industry point of view, it means that we have low development speed. So we cannot annotate, I don't know, thousands of images to create our prototype. Second, if we don't have enough data, likely our accuracy and quality won't be high. And finally, if it's too hard to annotate even one pathology in, I don't know, 1,000 of images for COVID, it's much harder to annotate several pathologies, right? It just, you need proportional number of resources. And this is partially explains why we have only narrow solutions. For example, AI just for lung cancer. So we cannot do anything else, just lung cancer. It's an important problem, no doubts, but still doctors have many other duties. Second, in that this data, usually you have an agreement with a hospital or maybe two hospitals, and then you can take their data, annotate it, and use it for training. But the problem is that distribution of the data into meanings, distribution of technical parameters and distribution of population is really, really narrow for every hospital. This is an example of technical variability. So the top row is lung CT of the same patient. I'm not sure that it's the difference between images are clearly visible during the translation, but the difference is that the left one is really smooth, without noise and with some smooth borders, and the right one is quite sharp, with higher level of noise and with rougher boundaries of, for example, of this lung. MRI, it's the bottom row, is even more sorry. MRI changes is even more dramatical. So this is these are different patients, no doubt, but still this is the same type of MRI examination, so-called flare images. And you see that that there is a non-linear change in intensities. For example, in some images, like the most left one, the skull is bright. and the brain is dark. For the central one, vice versa, right? The brain is white, the skull is quite dark. So obviously, it's really not hard to predict. If you train your model, for example, on this event or MRI machine, then we'll try to predict on symphony, then you will likely fail. And what is more important, it's not the difference, not only the difference between the, say different manufacturers. The second and third examples are the same MRI machine installed in two different hospitals with different parameters, and you see the difference in images. And as for population, imagine that you usually, okay, we want to create a tool for example, for tuberculosis. Where can I find the data? Okay, I need some tuberculosis hospital, right? Then every, I don't know, second patient in the hospital has these signs of tuberculosis. But when I then try to transfer this AI product to an outpatient hospital, then likely a very small number of patients there will have this tuberculosis. So this is about this kind of too narrow distribution of patients within a specific hospital. And yeah, this is an example for the CT, how it affects the quality. So this is in blue here is shown the predictions of network trained to segment COVID lesions. And obviously it should be within lungs, right? But when we change the protocol from training domain to a new testing domain, you see that some really strange predictions outside lungs even happen. So it's just an illustration of the effect, even for this, well, not really significant changes in images, how this shift affects the quality. Okay, so this is another example, pretty interesting one. This is not our example. It's a paper published actually 4 years ago. They studied a really simple imaging modality, chest X-ray. In contrast to what I said about CT and MRI, chest X-ray is much simpler modality in terms of the number of available images, even publicly available. So you see, it's now not hundreds, and even not a couple of thousand. It's 150,000 of images. So there are a lot of images. Second, it's just simple two-dimensional grayscale images. So it seems that it's really, really straightforward to use some ideas from mainstream computer vision to work with these images. So the researchers used two data sets to train the model, and then tried to predict on a different hospital. And you see the area under the ROC curve drop significantly, right? And when they try to study is it about kind of technical parameters, or maybe it's about patient population, as I mentioned before, they conducted a really simple experiment. They trained the same network. I don't remember, likely it was something simple like VGG, or I don't know, ResNet maybe, to distinguish the hospitals. So can network understand, is it from one hospital or from another one? And here is the attention. You see that it pays its attention to not to some I don't know, some different patterns in lungs or other clinically relevant parts of the image. Instead, the most informative feature is this label. So it's left, to understand where it's left and right on the image. Another really cool example of some unexpected behavior of a pre-trained neural network is this paper. So it's even simpler. It's not images collected by some special device like X-ray machine or CT machine. It's more or less skin photos, not exactly, but close to. So here, the design of experiment. The researchers selected some images and added these marks. So this is image without marks, and the same image, the same part of the skin with these marks. So why did they do this? It's because then when kind of standards the standard procedure is to for a doctor, I mean, is scan the whole body and mark some suspicious lesions with this marker to return later and to analyze it in details, etc., etc. So it means that in the training sample, they have both marked and unmarked lesions. And for this experiment, they created two versions of the same lesions with marks and without marks, and then analyzed the attention. So when we didn't have marks, then the network, this is attention for this image. So the attention is something inside this area, right? It seems reasonable. But when they added these marks, now the network completely or almost completely ignored the actual lesion and concentrated on these two marks. And yeah, for some reasons I forgot to include the numbers, but the drop was significant. It's kind of specificity dropped from around 90-something to 50%. So it's really huge gap. Especially, I forgot to mention, this is about a medical device with CE marked, so clear to be used in Europe as medical device. So again, this is an example of how different, even unclear shifts may affect the quality. And from industrial point of view, it's obvious it's lack of reproducibility, I mean, on different data sets, and as a result, additional regulatory barriers. So more advanced verifications of the quality with different data sets, etc., etc. So again, it's slowing down the industry. Okay, now let me briefly cover some of the possible solutions. So I mentioned two main problems. So the first one is lack of annotated data. The second one is domain shift. And I will give some examples of research which we did, or actually we still do in some areas, to explain how can you address these challenges, in my opinion. So let me start with the one of the most actually obvious solutions of lack of training data. Okay, imagine that we don't have the binary masks for segmentation, or at least a lot. Imagine that we have just a couple of dozens, as we did. But we can extract, using NLP, we can extract overall classification label from the protocol created by a doctor. So we can mine thousands of images without pixel-wise labels, but with just image-wise label. So in other words, for this particular study, we had around several dozens of segmentation masks and around 1,000 of classification labels. So for 1,000 of 3D images. And our goal was to create a system to triage patients, so to sort patients, to highlight patients with a high percentage of affected lungs and with high probability of COVID, to be actually sorted and directed to some specific treatment. And we created some actually unit-based architecture with attached classification head, and we compared several setups. So what is the right map to do? Which is the right position of the within the network, so within the unit segmentation network, to classify images? And the most obvious answer is that here at the end of the network, we have really good features, a really good representation of what is going on with a lot of semantic information. And the most reasonable way to add this classification head with corresponding loss function is to use this part of the network. But surprisingly, we compare it with other positions, and with this one, so with the less spatially detailed information, with a pretty rough spatial resolution image in this bottom layers of the unit. And surprisingly, but this idea allows us to achieve much higher accuracy in several classification problems. One of the most interesting parts of this table is that we compare not only with healthy lungs and with lung cancer lungs, which was included into the training data set, but we also compare the network with using a data set with bacterial pneumonia. So it's a different type of pneumonia with different pattern. And this data set wasn't shown during the training. So the network didn't know anything about the bacterial pneumonia, but still the quality of classification was really good for this idea. So there are some reasons behind this result why, but it's not really important for our purpose. As for the industry, actually, I mentioned that in 2020 we identified the opportunity, and we conducted this research, and then we created a product based on the algorithm, basically quite similar to what we described in the paper, with some additional tricks and some other databases, but still it's really close to what we described in the paper. And I forgot to mention it was published in Medical Image Analysis. This is one of the top two journals in the area. So we competed with 15 companies in 2020, and we were selected as leader. And also, based on measurements, we saved up to 30% of radiologist time in more than 100 hospitals. Okay, so the next part, how can we address this lack of training data, is to exploit domain knowledge. Let me explain what I mean. This is another problem. It's vertebral fractures detection. So now we see the same 3D image, but now with a different slicing kind of. So now we slice patient in different ways. So it's kind of from one side, right? Not kind of cut the patient. And the problem is that we need to look for vertebrae which are deformed. So this is a normal vertebra, and if the mineral density is low due to osteoporosis, then it can be deformed. And this is kind of the examples of these severe fractures, severe deformations. And you can see the real example here, this one. So the majority of methods are based on either on classification or segmentation. So they first segment the spine, then try to extract some features, and then to understand is it kind of compressed vertebra or not. From industrial, or actually maybe from doctor's point of view, these approaches are kind of black box. They do not understand how to interpret it. So, okay, this is a map of attention. Okay, I need to see here, and what about this one or this one? What is it? The same for the segmentation. And the reasons for example, for wrong predictions are absolutely unclear. What we propose to do is to create some specific algorithm. It consists of two parts. So first, in 3D, we create a network to reconstruct this spine center level. spine center line. So just a single curve in 3D. Then we have this curve. This is the first network. Then we can create a simple two-dimensional image of the vertebra, kind of by straightening the backbone via this curve and to selecting the center of projection. And then for every vertebra visible on this now 2D image, we want to estimate 6 key points actually related to different types of deformations. Then we can measure this particular quantity. It's the fraction, it's the ratio between height loss. So for normal, you see that all 3 heights, this one, these ones are almost the same. When we see some signs of osteoporosis, that these heights are different, and these are numbers suggest the relevant difference between these measurements. So to reproduce these numbers, we need to calculate these 3 heights, or we need to localize 6 key points. And we created kind of its combination of detection and key point localization within one network. And again, here is the pipeline. So the first one is the curve in 3D, then this small image, small 2D image, then simultaneous detection with key point localization with some specific loss function inside. And then we go back to the original image and mark, actually list these specific measurements required by clinical guidelines. And these outputs are really easy to verify. The doctors that just need to check, okay, point locations are okay, so likely, yeah, I believe that this is the correct measurement. This paper was published in Mikhail, the core conference in our field, and also currently under the final stage of review, extended version, again in medical image analysis. From industry point of view, it's one of my favorite examples because here we competed with Zebra Medical Vision. It's Israeli startup with good funding, about $60 million of US dollars. And one of the most interesting facts about this funding is that Professor Feifei Li, a Stanford professor known as the author of ImageNet. So according to Crunchbase, her only investment as a person was into this particular company, Zebra Medical Vision, back to 2018, I believe. So as I mentioned, we participate in this competition in Moscow with many participants, including Zebra. And they publish a lot of information about the results. For example, they publish the quality metrics of their independent testing. And we got almost ideal results from these tests, much better than Zebra got. And also you see the difference in interfaces. They all offers more or less a black box. We offers clear measurements with direct suggestions what to do with this patient. As a result, doctor's feedback is much better in our case. And also works faster, but it's not really important, but it's a nice outcome as well. Okay, so the next part is more computer science one, more modern, I would say. And we can try to work with a huge amount of not annotated data. I had this number on the slide, but I likely forgot to mention, as a company, by now we process 1 million patient studies, taking into account that one study, one scanning is around 400 images to the images. It means that up to date, we analyzed 400 million of images. Obviously, these images aren't annotated. So self-supervised learning in this setup, if you have there's cloud storage systems where a lot of data is accumulated, it's reasonable to think about self-supervised learning as a way to address this lack of annotated data issue. So this is currently research in progress, actually, and the idea, yeah, well, actually, I mentioned that we have some segmentation labels for a small amount of data, around 100 of 3D images, and we have a huge amount of unlabeled data. And the idea is that we want to explore, can we create a reasonable solution for at least a reasonable pre-training for the full supervised learning. And the core difference with the mainstream self-supervised learning is that we need to create a local global representation. So we don't need to have just one feature vector for the whole image. Instead, we want to have feature vector for a single pixel or voxel, as we work with 3D pixels, voxels. So it means that we need to kind of a map of features for every voxel. And currently, we created actually right now pretty simple pipeline based on contrastive learning. We try to create these features, voxel level features based on kind of more or less common ideas from contrastive learning, that you need to, for every pixel, you need to select kind of a negative example and positive example. And there are several tricks. How can we do this? For example, we can use some simulated images using in order to simulate domain shifts, and I will cover this idea later in the separate part. So the basic setup is more or less straightforward, adopted to segmentation with some specific domain specific augmentation. So actually, when we selected this positive pair, we need to transform the original patch somehow, and it can be simple transformation like rotation or flip, or some intensity changes, or it can be domain specific augmentation. For example, we can simulate these different CT protocols to create this positive pair. And finally, this is current results for one short segmentation. So it means that we have just one annotated image, and we use extremely simple heuristic. For every pixel for our new test image, we just look for the closest. So it's a kind of K nearest neighbors, right? The closest pixel in this feature space, and then just assign the same label. So if it's ground truth label for the most closest pixel is 0, okay. So for this one it will be 0. If it's more than if it's 1, so it will be 1. So it's binary segmentation problem. I forgot to mention, sir. And you see that even this extremely simple algorithm, we do not do some tuning above the obtained feature maps, just the nearest neighbors. Actually, the output mask is really good. So it's kidney. So this kidney for our test sample. This is a ground truth segmentation map. So there are some minor mistakes, but for this extremely simple procedure for actually segmenting the new image, I would say the result is impressive. As for some metrics, so again, it's kind of research in progress. What I showed before, it's published papers. This is ongoing research. But we see that, again, if we apply fine-tuning strategies, that the result, the quality is much higher for this pre-training. And from industry point of view, we expect much higher development speed for initial releases, so for MVPs. but we still need to measure the real effect. I guess that we have 11 minutes left, so I will skip this part about domain adaptation and will briefly, and likely domain generalization, briefly cover out of distribution detection. But before I do this, I guess that it can be useful to describe the different problem statements. So the most classical supervised domain adaptation is the following one. So you have a lot of examples from your training domain, annotated examples, and some examples, a few examples from your target domain, again with annotations, right? And then you need to create a model which is robust for this new domain. And supervised domain adaptation, in contrast, here we assume that we don't have labels for our target domain, but we still do have some images from this domain. And again, we need to do this. And we have some research about these two problem statements. But likely the most important one from an industrial point of view is domain generalization. We want to create a product, then we need to certify it, for example, to get FDA approval or CE mark, and we cannot collect and retrain it for every hospital, right? Product must be fixed. It's a pretty strict requirement. So we want to create a generalizable solution. So we can assume that we have several sources, 1, 2, 3, 4, and from these sources, we want to create a robust model for source number 5, number 6, number 7, even if we don't have examples from these domains. Okay, I will skip this. These are some examples. Yeah. So the last part here is out of distribution detection. So it's a possible solution okay, we know that our product have some limitations, right? We know that we cannot process, I know, some specific patients or some specific protocols from CT machines. But we need to openly say about this. I mean, the product must show that, okay, I know that this is out of my I don't know, training-based requirement, etc., etc. So I cannot process it. It means that we need to identify this out of distribution images to equip our product with this right to reject feature, right? I mean, reject to predict. And this is an example of what we did recently. So actually, we started with creating a benchmark for OD. We decomposed OD into several. Actually, I have some very simplified example. So we decomposed all possible OD, so domain shifts in different imaging. And so actually, there are 3 main reasons in real data. So the first one, we actually discussed it a lot, is different scanning protocol. The second one is that it's different patient population, right? For example, COVID-19 is a really good example. A lot of lung cancer products had really hard times when COVID, when they started processing COVID images, because it was a real shift in patient population. And finally, due to some just manual mistakes and mistakes in information storage protocols, transmission protocols, we can receive actually a different body part for analysis. For example, instead of chest, we can receive brain or abdomen. So we decomposed this, and then we researched some really cool computer science methods, both published and proposed by us. But then we identified a really extremely simple way to identify OD images. We need just to normalize image a little bit and then create a histogram of intensities. And then, according to our results, we can solve all our setups. These are real setups, and actually I briefly covered, with almost ideal quality. So it's kind of it's rock, so it's the almost ideal sorting of inliers and outliers. And we also participated with MOLOD challenge this year at Mikhail. It was a little synthetic. I mean, instead of real examples of domain shifts as we tested and as we proposed, they created some quite artificial benchmarks. And for example, they just randomly shuffle some voxel intensities, or they flipped the image. And even despite histograms obviously cannot detect both flips and both changes, just shuffle of voxel intensities, we still got the second place within this competition. And this is kind of result announced today because Mikhail is ongoing right now. As a final final example of ORD, this is the image which was submitted to all 15 companies in Moscow in 2010 to COVID-19 algorithms. So you see some kind of something similar to round glass opacities inside this object, and the legend says that only one product didn't segment this as COVID, and it was our product. So we don't know exactly is it true or not. And we, during several months, we were sure that this is just a joke from radiologists, from Moscow radiologists. But then we, using actually OD, we found this case in our database. So at least one part is true. They really submitted this. Actually, it's trash can, so it's metal with some pedal here and with some I don't know, paper or some trash inside. It's a funny OD example, but still, I like it because really good indicator that many products really lack some really basic functionality in terms of for example, for doctors, right? They clearly see that this is not lungs, and we shouldn't segment anything here. Thank you for your attention. I hope that we have some time for questions, if any.
Thanks a lot, Mikhail, and it was very interesting, and the last example is amazing. Yeah, we have some questions, and I encourage colleagues to ask more. So, and the first question is as follows. So, how to avoid how to avoid collapse for pixel level contrastive learning, and how the model inductive bias helps with creating meaningful positive negative at the pixel level. Yeser, he supposes, Yeser is asking this question, that at random initialization, pixel embeddings will follow a Gaussian distribution to a certain extent.
Well, so there are several questions actually inside. As far as I remember, there is a paper about ImageNet where they tried to, on self-supervised learning, they tried to create some feature representation on an n-dimensional sphere, and their learning was pretty simple. They tried to maximize the average distance between all images. And so without actually any contrastive learning stuff like with positive and negative pairs, just like they wanted to maximize the average distance. As far as I remember, it was the averages, but anyway, the distance between all images. And the result was that it was easier to group close images, for example, lions and tigers, together, and to remove far from them, I don't know, some birds. I mean, it was optimal in terms of the loss they used. So a network trained some reasonable actually embedding just by trying to move this stuff in a different way. So I believe that here it also depends on the loss function, and in some actually there are a lot of technical questions behind this stuff. And when we started, we had actually terrible results. It was, in terms of learning, it was the learning curves was terrible. So it seems that kind of more or less tips and tricks plus some reasonable selection of loss function rather than some fundamental problem. I mean, this collapsing. Like I forgot the last part of the question. It was it consists of several parts.
Yeah, the second, you may look actually in Q&A, but I also can tell you
okay.
that the second part was that how the model inductive bias helps with creating meaningful positive negatives at the pixel level, which means a bit complicated formulation.
Yeah. Yeah, I believe that likely it's yeah. Well, no, it depends. It depends on what we want to achieve by the end. When I mentioned that, at least the most interesting part of this research, ongoing research for me, is related to this some domain-specific augmentation. And I'd like to cover why. So again, it's maybe not the direct answer to the question, but I think it's a good moment to discuss. So it depends on the problem we want to achieve, we want to solve. So the first one here, I concentrated on just accelerated learning of new networks. So we have a good pre-training, and that we want to learn a network faster. But it also can be combined with domain generalization. So if I can create some really robust representation of pixels, even for a different scanning protocol, I want to push the network to create the same representation for pixels, for the same pixel from, say, smooth image and rough image. And in some sense, this pre-training, this self-supervised learning, can also be used to not only to accelerate the subsequent supervised learning, but also to make models robust. So this is the most interesting question related to this part. So here again, what we've already did, it's more or less classical contrastive learning with some tips and tricks, with some technical issues, at least at the beginning. And what is interesting for me is to try to combine self-supervised with domain adaptation. So I mentioned that it can be achieved via some domain-specific augmentation. So it would be really interesting to check whether it's possible or not. So again, sorry for answering different questions, but I just want to highlight where the core interest for me. So I mentioned at the beginning that, well, my current occupation is CEO. I know that I have much smaller amount of time to study papers now, and but I have strong team, and I try to push them into some interesting product directions, rather than some pure computer science research. I try different loss function and try to increase the accuracy of pre-training by 2%. Instead, I'm interested in some different problem statements, I would say. So self-supervised plus domain generalization looks achievable and definitely really interesting.
Okay, thank you. And yeah, so I don't see more questions. Colleagues, if you have, please write, but I also have question on my side. So the majority of the experiments you have done, they were based on data from same city, where I would assume that population is relatively homogeneous. However, well, in the ideal world, we want to we build a model on some data, and then we probably want to distribute it, say, to the developing countries, or just, I don't know, to other hospitals in different parts of the country with different population, where they don't have capacity to train their models. So are there any like studies of the on the quality and the changes that happen to this method when applied to different, say, age group, racial
Mhm.
groups, and so on? And so what do you know you can tell about that?
Yeah, actually, this is a perfect question because I mentioned kind of one of the key challenges for the whole industry is that actually uh, accuracy of models of products can be much lower than declared. I mean, declared by the developer. So during the talk, I mainly showed results from our papers, and usually we use public data sets collected in states mainly, some in Russia, and we, at least by now, we haven't seen a huge difference related to population. I don't know, Caucasian, Black Asian. Likely there are some differences, but right now this is not the key factor. What is really important is different scanning protocols. For example, computed tomography can be low dose computed tomography, usually used for screening. So it's a healthy patient, actually a healthy participant, but with some high risk of, for example, lung cancer. And usually you cannot do just normal CT for this patient, for this person, because he or she is not ill, right? And you need to do low dose CT. And the difference in low dose CT protocols is really huge between countries. So it's again about scanning parameters, but just a different example. As for different age groups, it's really important, a really important question. And we do have some studies, internal, not published yet. Some studies was conducted by Moscow Healthcare Department. They just use our tool in an automatic mode and then sometimes notify us about the results, sometimes not. And we, again, right now, we do not see a huge difference between performance in different age groups. But indeed, it can be really important, especially if we selected, I don't know, just patients over 60 years for training with some specific age-related changes in their images. And then we will try to apply it for, I don't know, 18 years old patients with COVID, for example. So to summarize, right now, we do not see significant issues related to different races, for example, but we do see huge impact of different patient population, for example, COVID versus non-COVID, or some specific oncological hospital versus an outpatient clinics. And the most severe impact is scanning protocols.
All right, thank you. Yeah, and There is a small question in the chat. So what is the best way to commercialize these AI tools, in your opinion?
Well, it's a really slow process. So more or less typical pipeline is approximately the same. You need 2 years to develop the product. Then roughly speaking, 2 years to get your FDA approval or CE mark or equivalent. And then you need another 2 years to identify the ways to reimburse. So to change some flow of money in the healthcare system to get your reimbursement. So it's really slow process, and that's pretty interesting. That Zebra, I mentioned this company. It was acquired recently in the end of 2021. It was acquired by a public company, and as a public company, they must release all their profit statements. And interesting that Zebra, who works in several countries, in the US, they have FDA, they have CE mark, they work in the UK, in Israel for sure. So the total revenue was 2 or 3 times smaller than we got in Moscow. And the reason why is that this Moscow competition is really unique and strange for state projects or for kind of official projects, at least in Russia. They decided to reduce regulatory barriers. They say, okay, if you don't have the approval, but you do have a good product, and we will test you. So if the product is good, then we will allow you to work with real data, with real doctors. And so they reduced this regulation. Second, or replaced it by their own internal center of competence and some their tools and ways to validate the products. And second, they say, okay, we understand that you need money, and so we can offer you some reimbursement. It's not really huge. It's around $2-3 US dollar per processing. In contrast, for example, in states currently just discussing, and it's not implemented, just discussing. Reimbursement for the same pathologies, for example, vertebral fractures is around the amount is around $80. So the difference is huge, right? 40 times, 2 versus 80. But still, the speed of the process, right? That in Moscow it was created a really unique situation with reduced regulation and with available reimbursement. And this is why we have a lot of startups here. As for the globally, well, it's still a really slow process, but it's really important to, from the early stages of your development, engage clinicians and trying together with them to understand the clinical value. The most successful companies in terms of reimbursement, there are some examples. They have extremely simple way to explain why they need to be reimbursed. And usually it's not related to, I don't know, we can save some time for radiology. Usually it means that we can optimize patient routine, or we can reduce costs for average costs for patient routine. Even if you will pay us, we still can reduce it. And this is the core part, I would say, the right product, so the right, problem, and the product should be good enough to show this difference in terms of, ideally, in terms of money saved for healthcare system, or much better clinical outcomes for patients. And this will, at least as far as I see it, accelerates the process of getting reimbursement.
All right, and we have one more question in the chat. So probably the last one considering the timing, but it's really the long question, again consisting of several ones. So the first part is that how accurate should models be? Because some organizations claim 87% accuracy, and it seems to be the risk for patients. Can we get to 100%? And the second, okay, yeah, the first part is separate. Can you answer?
Let me start with this one. So it's a really important part, and what we know. So Moscow, they decided they use the area under ROC curve as the core quality metric to make decisions. It's not. I'm not sure that this is the best way, but still they selected this error under ROC curve. Then they introduced some thresholds. They say, okay, if your ROC score is less than 0.8, then you cannot participate in our project. And I mean, ROC 0.8 calculated by them on their internal hidden test dataset, not available to companies. Then our products got one product got 0.93, and all the remaining 0.98, 99, and even ROC equal to 1. So ideal classification. So it's definitely possible to achieve. But if we return to, so ROC measures just the quality of patient sorting, right? That we can classify that this image is with pathology and this is without pathology. But I'd like to return to this image. That this is just one part of the problem. For example, imagine that we want to look for lung cancer, and lung cancer is a really tricky problem. And we can say that this study have really high probability of lung cancer presence. And in terms of this metric, the result will be, I mean, ROC binary classification, the result will be really good. But then, in order to route the patient, you need to estimate the number of lesions and the volume of each lesion or each nodule. And if you miss, for example, 2 out of 3, it means that likely you miss multiple metastases, and it's completely different lung cancer staging, and it can be completely different pathway. Or you did the measurement, I mean the segmentation wrong, and then the volume, which is the most important part, is incorrect. And instead of sending the patient to the oncologist, you will send it to home and with the recommendation to repeat the scanning in 1 year to check is it growing or not. So there are many metrics behind, but if we concentrate on just classification, then we see that at least in Moscow tests, usually our performance, our internal tests or our clinical feedback usually concentrates more on, for example, segmentation quality, they call it localization, rather than just binary classification. So our products, we see that really high classification scores are definitely achievable. We also understand that localization quality also can be improved, and it depends on, again, on regulation barriers. If you have this really long cycle I mentioned, right, 2 years to create your first version of your product, then 2 years for FDA, and then you start receiving product feedback. Then you can create a new version of the product, and then you need again get a new FDA approval. So this development cycle is really slow. And this is one of the reasons why the quality is increasing actually with a pretty slow rate. Again, Moscow is a good example how it can be resolved because they don't require this regulation. So it means that you can, and they also provide a massive amount of feedback. So without hundreds of doctors work with our product, and they have some special forms to submit some from really simple feedback, like I don't agree with your algorithm in this case, and we need to analyze ourselves what is the problem, or it can write some description that it's better to do this in this way or that way, and it accelerates the process. So I believe that though right now Geoffrey Hinton is not right, still I see the possibility that in the next 5 years, at least products will be good enough to significantly accelerate the process to optimize patient routing, and maybe not replace radiologists, but eliminate this shortage. Because still there are a lot of problems. For example, again, sorry, it's a long answer, but I think it's a really important part to mention because it's also a really interesting research direction. So right now, we usually analyze images in a supervised setting. So we know that we want to look for lung cancer or COVID or something else. But the number of pathologists is fixed as we train our networks in a supervised manner. But obviously, a doctor can identify hundreds of different pathologies, and likely we cannot create a supervised solution for all of them. And this is why, for example, we cannot replace the radiologists. We can accelerate it, we can streamline patient routing, but we cannot replace it. And a possible way to at least partially address this challenge is to create this OOD for pixel-wise level. So imagine that we want to analyze, in addition to some fixed set of pathologies, for example, lung cancer and COVID, we also want to look for some abnormal regions in lungs, which is not COVID, which is not lung nodules, lung cancer, but it's definitely not a normal lung. It's something wrong with this. And then it can also be a really interesting and important product step. And obviously, it's an important research question, how to create a reasonable pixel-wise abnormal detection. Yeah, sorry, the last part was completely irrelevant, but it seems important for me.
Okay, great. I suggest that considering the timing, we need to finish here, and I want to thank you for this extremely interesting talk, and hope to see you in the future again at some of our seminars with new results. So thanks a lot and take care.
Yeah.